Let's talk about Euclidean or absolute space. So the way I define it is that it is something that exists out there. We all share the same space. All humans, every particle in this world exists in a common space. If you find 2 points in space, you can always calculate the distance between them. Now, if you assign a Cartesian coordinate system and imagine the points to be infinitesimally close, you can always calculate the square of distance as dx squared plus dy squared plus dz squared. We call this term a metric, and this is invariant in absolute space. Now let's talk about absolute time. So time is defined as a one-dimensional Euclidean manifold. It is a fancy way of saying that it is a continuum of points in one dimension. You can think of it like an axis, and every point on that axis corresponds to a certain point in time. Again, we all share the same timeline, and you can also define a metric in absolute time, which is invariant. What I mean by invariant is that it remains the same no matter where the observer is. But surprisingly, this notion of space and time is not correct. So along came Einstein and he said, no, this is wrong. According to him, we don't share the same space and time. So there is no absolute metric in either space or time. But there's an absolute metric in four-dimensional space-time. For this, he introduced a new interval, a new metric, and he called it the space-time interval. So the space-time interval is defined as dx squared plus dy squared plus dz squared minus c squared dt squared. Here, c is the speed of light. And we all know Einstein's famous postulate. The speed of light for any observable remains the same in all inertial frames, irrespective of the speed of the observer with respect to the source of light. Now, the claim is that this spacetime interval is invariant in all inertial frames. By the way, when I say an inertial frame, I mean a frame of reference in which Newton's laws are followed. Okay, so now let's try to prove how it works. Consider 2 points in the four-dimensional spacetime. We call these points events. To prove that the spacetime interval is invariant, we will consider a special case. So consider E1 to be the event such that a photon leaves the point, and E2 be a neighboring point in four-dimensional spacetime such that the emitted photon reaches it. Now, if we write the spacetime interval between these two events, we'll write it as dx squared plus dy squared plus dz squared minus c squared dt squared. Note that the first three terms correspond to the physical distance between the two events in a particular frame, and c squared dt squared refers to the square of distance covered by a photon. In this case, since the events itself talk about the leaving and arrival of a photon, this spacetime interval comes out to be 0. Now let's consider the two events in another frame S prime. When we write out the metric, we remember that the speed of light remains constant in all inertial frames. So this metric must also evaluate to 0. So using this, we come to the conclusion that whenever ds square is 0, ds prime square is also 0. And since we are dealing with infinitesimally small quantities, it's a fair treatment to write ds square is equal to some alpha times ds prime square. Now, alpha could depend on many factors. We just need to figure out alpha and we're done. So, alpha could depend on the spatial coordinates, the time coordinates, and the speed of the frame S prime with respect to frame S. If we think about it, we're talking about the relation between the metric in two different frames. It shouldn't depend on where the events are occurring in space or time. So we can safely say that alpha does not depend on the spatial or the time coordinates of the events. But it must depend on something that is intrinsic to the frame of reference. And yes, we consider alpha to depend on speed. So let's go ahead with that. To find out the exact expression for alpha, we consider three different frames. I call the first frame frame S, and it's a stationary frame. Then there's the frame S prime, which is moving with velocity v prime with respect to frame S. And we have the frame S double prime, which is again moving with velocity v double prime with respect to frame S. We can write the relation between the metrics in frame S prime and S, and also the relation between the metrics in frame S double prime and S. We take the ratio of those two metrics and we end up with alpha of v prime divided by alpha of v double prime. But we can also write the same relation for the metric between frame S double prime and frame S prime. Here note that v is the velocity of frame S double prime with respect to frame S prime. Using simple algebra, we end up with the relation alpha of v is equal to alpha of v double prime by alpha of v prime. So this is something strange. Remember, we are talking about speed and not velocity. Now, the value of v depends on the way v prime and v double prime are arranged with respect to each other. For alpha of v to depend on the ratio of alpha v double prime and alpha v prime doesn't make sense unless alpha does not depend on speed. And since alpha does not depend on speed, using simple algebra, we can say that alpha is equal to 1. And there we have it. We have proved that the space-time interval in frame S is equal to the space-time interval in frame S prime. We have shown that the space-time interval really is invariant.